Okay, we are in the process of applying Schrodinger wave equation to model systems. We did first we did free particles, then we did particle in a one-dimensional box, and then I extended the concept to a two-dimensional surface also. Okay, now if you go for particle in a one-dimensional box, and for particle in a one-dimensional box, we derived the equation of normalized wave function root 2 by a sine n pi x upon a, and we derived the energy equation also as n square h square divided by 8m square. Then I talked about its application into conjugated diene molecules, that how you can find out the wavelength for of the radiation which is required for emission or absorption of such conjugated diene molecules. Okay, and then I extended the concept to two-dimensional box model. But one thing which we also talked about, that if we know the wave functions, normalized wave functions, then we can find out the expectation value of position and expectation value of momentum. This we derived. Okay, and I said you that the expectation value of position is a divided by 2 and expectation value of momentum is 0, and then I said you that it doesn't mean that the particle is at rest, because the lowest energy which is possible, which is called 0 point energy, is h square divided by 8m square. It is not 0, because the lowest value of n which is possible is 1, it cannot be 0. So the lowest energy available, and this is called 0 point energy. So if the molecule has energy, the particle is not at rest, but even then the momentum comes out to be 0, the average momentum. So what we say is momentum within the angular bracket is the average value, or expectation value is not just one specific value. Out of the several measurements, some momentum will be the positive momentum, and another will be in the opposite direction. So that we talked about that when wave function is represented by exponential I kx and plus b exponential minus I kx, how the momentum, the value of a and b decides that if a is 0, what happens, and if b is 0, what happens. The momentum changes the side, because momentum is a vector quantity, so direction changes. So the same thing happens here. Out of the multiple measurements, some momentums are positive in the positive direction, some moments are in the negative directions. Okay, so this we talked about. If we extend this concept to a little more, and we try to find out the position of x square, then the easiest thing to do is that you simply put those values root 2 by a sine square n pi x upon a into x square, because, and get the value of this one. Because why it is so? Because the expectation value, for the expectation value, what you do? You do root 2 by a wave function sine n pi x upon a, then you write the operator which is simply multiplying by x square, and then again root 2 by a sine n pi x upon a into dx. Okay, so this will give you the square of the position, expectation value of the square of the position. So this we can find out, and for finding out this value, what you do? You convert this 0 to a x square, and this we can write as minus cos 2 n pi x upon a 1 over 2, you can bring this side, into dx. Okay, and if you, so you write 1 over a, and then we have two integrals, 0 to a x square dx is one integral, then you have another integral 0 to a cos x square cos 2 n pi x upon a into dx. This you will do yourself, it is integration by part. Okay, and this will be x cube divided by a cube, and if you put 0 value, then it will be 0, and if you put a value, it will be a cube divided by 3. So if you solve this equation, you get the position of the square of the position, and the value which you finally get is a square divided by a, sorry, When you solve this equation, you get a square divided by 3 minus a square divided by 2n square pi square. This value you should get for the momentum, for the position, square of the position. What will happen if you calculate the square of the momentum? If somebody asks you find out the value of px square, then again the rule remains same, that you write the wave function root 2 by a sine n pi x upon a. Why I am doing all this? Because these are the things which you will be do time and again with different wave functions in quantum mechanics. So we are starting with simplest problem, we are doing it time and again, so that you are sure you don't have any issue in the later on. Okay, so here it will be the square of momentum operator, and then you will have root 2 by a sine n pi x upon a into dx. Now what is px? Momentum operator. Momentum operator is minus I h cross d dx. So what will be px square? It will be minus I h cross d dx, and this will be multiplied by minus I h cross d dx. So minus minus will be plus, and then you will have I square h cross square d square by dx square. Okay. So if you put this value here, then you can bring I square is minus 1, so you can bring minus h cross square outside. Okay. Knowingly, I am not taking this root 2 by a outside, n pi x upon a, and then you have d square by dx square of root 2 by a sine n pi x upon a dx. Okay. So if you solve this one, if you take the first differential, sine will convert into cos, and if you solve the second differential, then again cos will become sine. So within this integral, you will have this value root 2 by a sine n pi x by a and root 2 by a sine n pi x by a within the integral, which will be equal to 1. The only thing is that you will have to take care of is this part ax, twice it will be outside. Okay. So what will be the value of final value of px square? So the final value of this px square comes out to be h cross square n square pi square divided by a square, because one or negative sign you will get when you do the differentiation. So negative will become positive. So now you have all the values of x, which is a by 2, x square, which is just I have written a square divided by 3 minus a square divided by 2n square pi square, a square divided by 3 minus a square divided by 2n square pi square. Then we calculated the px value, that is 0, and we calculated the px square value, that is h cross square n square pi square divided by a square. Knowingly, I have not done a stepwise calculation. So all of you will who are watching this module should do it on your own, do every step of this section and convince yourself that after doing the calculations you get these values. Okay. Once you have this, then when I was talking about the uncertainty relationship, then I said you that uncertainty relationship, we can represent delta x and delta p x as a variance or a standard deviation, and the value of this I have given you is x square minus x square and then px square minus px square. If you put these values here, then finally then delta x into delta px comes out to be h cross divided by 2 multiplied by root under this you get. And what is this? You have pi a square. Pi value is 3.14. N can be 1 or greater than 1 always. Okay. So n is equal to 1, 2, 3 quantum numbers. So if you look at this value, it is 3.14 square. So it's greater than 9 even if n is equal to 1. So if you divide n.1 this pi square divided by 3 will always be greater than 3. Okay. So 3 minus 2 will be greater than 1, means this value is always greater than 1. It means if you multiply h cross a square, then this is always greater than or equal to h cross divided by 2, always greater than, and this is what is Heisenberg uncertainty principles. So if you apply Schrodinger wave equation, if you apply quantum mechanical postulates, you find out the average value of position, you find out the average value of a square of the position, you find out the average value of momentum, you find out the average value of the square of the momentum, and then you plug in these findings into the equation delta x into delta px. The result which you get is that delta x into delta px is always greater than h cross divided by 2, and this is what is uncertainty relationship. So with any other system also we can do, we will do it for simple harmonic oscillator also. Okay. So uncertainty relationship is a direct consequence of quantum mechanical application or Schrodinger wave equation application to simple system. Okay. So this I wanted to convey. Then I extended this concept of 1D box to 2D surface yesterday, and I said you that we can talk about a square surface or we can talk about rectangular surface. I introduced the concept of degeneracy and how degeneracy is lifted when you go from this to this one. This we did yesterday. Today we will extend the concept of particle in a one-dimensional box to three-dimensional box, and here one thing additional I will do, that I will write the detailed equation starting from the very beginning, and we will do separation of variable also, because separation of variables you will have to do when we will apply Schrodinger wave equation to rigid rotor also, when we will apply Schrodinger wave equation to hydrogen atom also. Okay. So start doing this. We did this in the when I was deriving the Schrodinger wave equation also, but start doing this for the particle in a three-dimensional box. So we will write particle in a three-dimensional box. For a three-dimensional box, the Schrodinger wave equation which you can write is del square psi we have supposed for one-dimensional box V is equal to 0. So let here also V is equal to 0. Now here since you have three dimensions x, y and z, so your psi is a function of three coordinate x, y and z. Whenever you have a wave function which is dependent on more than one variable, then what you can do is you can split this wave functions into component wave functions, each depending on only one variable, and you can write the total wave function as a product of this component. Okay, so this is the general things which you will be doing time and again in quantum mechanics. So what we do, we split this psi into three functions: capital X depending on X only, capital Y depending on Y only, and capital Z depending on Z only. So if a wave function is dependent on more than one variable, split this function into component wave function, each depending on only one variable, and the total wave function is the product of these component wave functions. So that's what we have done. Okay. Now in the same fashion, we can write the energy also. We can split the energy. Energy will also depend on different variables. So energy also we can split into component energy Ex, Ey and Ez, and the total energy will be the sum of the energies. If you put these values in this equation, you know that it is Laplacian operator, which if you write, then del square by del x square plus del square psi by del y square plus del square psi by del z square plus 8 pi square m by h square E into again E psi is equal to 0. If you put these values for energy and wave function, you plug in these values into this equation, what do you get? What you get is d square by del x square, x into x, y into y, z into z, plus del square by del y square, x into x, y into y, z into z, plus del square by del z square, x into x, y into y, z into z. Plus we can write 8 pi square m by h square Ex plus Ey plus Ez into xx, yy and zz is equal to 0. This I can write. Just I have put the value from these two equations. Now you are differentiating with respect to x, so y part and z part will be a constant. So you can bring this outside, yy and zz, and now you can write d square xx by dx square plus, again here you are differentiating with respect to y, so x and z will be constant. So xx part and zz part you can bring outside, and then you can write, and here you are differentiating with respect to z, so x and y you will bring outside, d square plus 8 pi square m by h square Ex plus Ey plus Ez xx, yy and zz is equal to 0. This I can write. Now divide this equation, each terms of this equation, by xx, yy and zz. Dividing by xx, yy and zz, you will see that your first term reduces to 1 over xx, because yy and zz will go, d square xx by dx square. Second term will be yy, d square yy by dy square. Third term will be zz, d square zz by dz square, and this term will be 8 pi square m by h square Ex plus Ey plus Ez is equal to 0. Okay. Now you look at this one. It is x dependent. This is y dependent. and this is Z dependent. Same way we can have for energy also. If you write this one, write this 1 over xx. Let me write it. Then this part we can write as 8 pi square m ex divided by h square plus 8 pi square m h square ey plus 8 pi square m h square ez is equal to 0. So, you look at these terms. This term is x dependent, this term is x dependent, okay. Then this term is y dependent, this term is y dependent. Then this term is z dependent, this term is z dependent. So, club these terms and you can write 1 by xx d square xx by dx, and all this is summation. So, you can sum this as like this one, 8 pi square m by h square ex. Then you can write for y, then you can write for z. And if each of these summation of two terms becomes equal to 0, then this equation is satisfied. So, we can write this is equal to 0, this is equal to 0 and this is equal to 0, okay. So, we have separated the three equations. One is x dependent, this is y dependent, and this is z dependent, okay. This is called separation of variables. Now, let us look at the first equation. Can I write this equation as we can write it, okay. And if you compare this with the equation of particle in a one dimensional box, it is exactly the same thing. So, that you can write d square by dx square plus pi square xx is equal to 0, where 8 pi square m by h square ex under root, okay. So, the solution will also be similar to the particle in a one dimensional box. So, for each of these equations, we can write the same Schrodinger wave equation solution which we have done for the particle in a one dimensional box. So, let us write it. So, for x component we can write your psi x will be root 2 by a sine. Now, I am writing nx just to differentiate, nx x divided by a. Then your ny will be root 2 over b sine ny, and then psi z will be where a, b, c is the dimension, is the dimension of of the box. Okay. So the total wave function also you can write as a product of these individual wave functions. So the total wave functions will be this we have written as xx, yy and zz. Okay. So if the product you can write as root under 8 divided by ABC into sine nx pi x divided by a sine ny pi y divided by b sine nz pi z divided by c. Same way we can write expression for energy also. So energy also you know what was the energy in the particle in one dimensional box, n square h square divided by 8ma square. So we will write Ex nx square h square 8ma square, Ey we will write as ny square h square divided by 8mba square, and Ez we will write as nz square h square divided by 8mca square. So the total energy which you can write is h square divided by 8m will be common, and then within bracket you will have nx square divided by a square plus ny square divided by b square plus nz square divided by c square. So this will be the energy. For particle in a 3-dimensional box, the total wave function is this one, and this is the total energy. In order to simplify this, what we can assume is that what is the cubical, for a cubical box what will happen? For a cubical box, A will be equal to A, B will be equal to C, and if you put these values, then your total wave function psi for a cubical box will become equal to root under 8 divided by a cube into sine nx pi x divided by a sine ny pi y divided by a sine nz pi z divided by a, because all sides are equal. So same way for energy we can write as, now h square divided by 8ma square I can take as common, and then it will be nx square plus ny square plus nz square. So look, for a one-dimensional box, if you compare this with a one-dimensional box energy, then it is root 2 by a sine n pi x upon a, and energy is n square divided by h square 8ma square, where n is 1, 2, 3, 4. So for a one-dimensional box you get only one n, for a three-dimensional box you get 3 n, nx, ny and nz are quantum numbers for particle in a three-dimensional box, whose value ranges is equal to either 1 or 2 or 3 or 4 and so on. Okay. So quantum number arises as a solution of Schrodinger wave equation, as an automatic solution of Schrodinger wave equation. You don't need to do anything. Okay. For if you take all nx and ny and nz equal to 1, nx is equal to ny is equal to nz is equal to 1, then what will be the energy? And we will write energy equal to E111, and it will be 1 plus 1 plus 1, so it will be 3 h square divided by 8ma square. What could be the energy for E? When I write 211, it means 2 is the value assigned to nx, 1 is the value, and the 1 is the value assigned to ny and nz. So nx, ny, nz. I am writing in this form, i.e. nx, nx, Ny and Nz. Okay. So what will be the value of 2, 1, 1? 2 will be a square of 2 will be 4 and plus 2, 6 will be 6h square divided by 8ma square. The next level, the next you can do is 1, 2, 1 and this will also be 6h square divided by 8ma square. And the third level will be 1, 1, 2 means here the Nz is 2. There also you have 6h square divided by 8ma square. You see all these are degenerate set of quantum state. Degenerate set of quantum state because all have the same energy, but the wave function will be different. For this, if I write the wave function, what should I write? If it's a cubical box, then I will write psi is equal to root under 8 divided by a cube, then sine, now nx is 2, okay, so pi x upon a, and sine, now ny is 1, so pi y upon a, and nz is also 1, so it is sine pi z divided by a. If you write wave function for this one, it is 2, 1, 1 and it will be 1, 2, 1. So this will be equal to root under 8 divided by a cube sine pi x upon a, because nx is equal to 1. Now here you will write sine 2 pi y divided by a, and here you will write sine pi z divided by a. Same way you can write for this one psi 1, 1, 2 root under 8 divided by a cube root under sine, now it is 1, 1, 2, so it is pi x upon a sine pi y upon a and sine 2 pi z upon a. Okay. So all these are different, wave function is different, but the energy remains same, and such orbitals are called degenerate orbitals, equal energy. Okay. So if you plot this, you will have the lowest energy level, that is E1, 1, 1. Then you have 3 energy levels, all of same, E2, 1, 1, E1, 1, 2 and E1, 2, 1. Okay. What about the next one? If you go for calculate E2, 2, 1, okay, then what is the energy? You just look at this value, it is 2 and 2, so 4 plus 4 and plus 1, 9, so it will be 9h square divided by 8ma square. And what could be the other alternative form? It could be 2, 1, 2 and it could be 1, 2, 2. So all this will have the same energy. So 3 energy levels again you will have, and it will be E2, 2, 1, 2, 1, 2, E1, 2, 2. Okay. And if you go for E2, 2, then 4 plus 4 plus 4, it will be 12. Is it possible to write another combination of the wave function? No, it will be singly degenerate. Okay, so this will be, so you see that it is triply degenerate, this is triply degenerate, this is single degenerate, mono degenerate, this is mono degenerate. Okay, so this way the concept of degeneracy which we introduced in the particle in a 2-dimensional box can be extended to particle in a 3-dimensional box also. Okay. Now the question is that how this wave function would look like. Okay, of the two-dimensional box and of the three-dimensional box. Okay, I will show you in the next module that comparison of the wave function of particle in a one-dimensional box, two-dimensional box and three-dimensional box. And up to now what we have supposed is that within the box potential energy remains 0 and outside the box potential energy is infinity. What will happen if the potential energy on one side is infinity, on another side it has a finite value? This also we will look. There are many variations which we will be looking. Okay, thank you.